right, so for the last item that we have here today, we're actually going to mix it up a little bit and make it kind of fun this afternoon. Should be a really good, spicy conversation. I've actually been looking forward to this one the whole day. Okay, so I want to introduce Bill, Lynn, Michael Krause, Chris Peterson, and Jonathan Hinkle. So Bill is from Dell EMC, Michael's from HPE, and Jonathan is from Lenovo, and then Chris Peterson's from Facebook. And we're going to have a panel discussion on NVMe SSD form factor challenges. Ooh, should be fun. All right.
Okay. Yeah, we decided to try and get some of the system OEMs and hyperscalers together to talk about basically what are our challenges when we have to incorporate these new SSD form factors into our systems. So what I wanted to do was, do a real brief, look at the history of some of these form factors. Then there's a section that has 8 or not, or actually not that many, about 5 or 6 different SSD form factors that are floating around out in the industry right now. And then we'll go into, what are the system challenges that we face as system designers to try and use these form factors in our various platforms. And we wanted to look at server platforms, hyperscalers, hence Facebook, and also client. Client ships a tremendous amount of NVMe. Okay, so if you go look at the history of form factors, I mean, storage goes back to, in 1956, they came out with the refrigerator. These were actually drums that encoded data on big magnetic drums. From there, in 1975, they came out basically with 14-inch discs that were the size of a washing machine. I'm not sure if many of you guys remember those, but they were really interesting, and they packed a walloping 92 megabytes. So in 1980, the 5¼ inch drive came out, and it started at 5 megabytes. Personally, I started with digital equipment back in 1982, working on 14-inch drives. The 3.5-inch drive came out in 1983. The 2.5-inch drive came out in 1988. And then we kept going the same route, 1.8-inch drives, 1.3-inch drives. The 1.3-inch drive didn't really last that long. But if you look at it, the bulk of servers shipped today use 2.5 and 3.5-inch drives. Those form factors have been stable for almost 30 years. So from a system, architecture point of view, we really haven't had to deal with a lot of change in the storage realm. It's a question of how many of these we can fit in. You can fit 24 2.5s or 12 3.5s. We really didn't have to think that much about it. In 2009, we started seeing SSDs come out in different form factors. In 2009 was mSATA, 2013 was M.2. So if you look at an HDD versus an SSD, an HDD is probably one of the most complex electromechanical devices on the planet. I mean, the physics involved of flying a head over that magnetic surface is mind-boggling. So the barrier to entry to doing drive designs was very, very high. I mean, you didn't go in and create a new drive form factor without a really, really good business case and lots of bucks behind this thing. If you look at an SSD, you essentially have a controller chip, a bunch of NAND, and a PCB. So just, not counting the firmware that's required on this thing, if you just look at the hardware, anybody with a CAD package in about, 6 weeks and $5,000 can create a new SSD. I mean, there's really not that much to it. So given that the barrier to entry for SSDs is really quite low, and I said I'm not counting the firmware in this, I'm just counting, putting the chips down on a board and packaging it up. It's really not that difficult to come up with a new form factor. Hence, we have lots of form factors floating around now. So we have, and they have real sexy names like SSFTA 1006. 1007, 1008, NGSFF. There's add-in cards, PCIe add-in cards. There's the traditional, 2.5-inch drive, U.2. And then the client guys have M.2. So there are lots of these form factors floating around now. From a system point of view, system OEM point of view, I don't want a lot of choices. There are too many choices out there. Each of them have their own pros and cons, but we really need to get down to something that's a little more manageable, like 1 or 2. Historically, we've had 2.5 and 3.5. Actually, the 2.5 works pretty well in a lot of cases, but it's running out of steam. So if you look at these new form factors that are running around, what I've done is I've included a slide on basically each form factor that's out there. And this is mainly for reference. I don't want to go through each one of these in detail, but hence, we've got M.2 out there that, a lot of people are using. It ships in massive quantities in the client space. It's a very serviceable form factor. We have the 2.5-inch SSD U.2. There's another version that's, some people call it U.3. There's some other names for it, but it essentially fits in a 2.5-inch drive form factor. That's very nice because you can interchange it with rotating media and an SSD. You've got TA1006, which is a small called Slim Drive. This was Lenovo's entry into the EDSFF arena. We have TA1007, which is sometimes called the Intel Ruler, donated by Intel. We have TA1008. This is a form factor that has several variations defined within the specification that was donated by HP and Dell. This one is, if you think about it, everybody's like, well, that's not one, that's a whole bunch. Well, if you look at a 2.5-inch drive, if you go back and look at the specification for the 2.5-inch form factor, it has lots of variations too in thickness and other things. So this is sort of a table that I wanted to throw in that sort of compares the different sizes and power and amount of flash you can put onto these various form factors. This is another informational slide that I wanted to throw in there. I don't want to go over this in detail. And, depending on who you talk to, they may argue a little bit about, well, this one really can fit, 25 NAND chips on it, not 24, But this gives you sort of a way of comparing the various sizes of these things. So what I wanted to do was get into, this is sort of the meat of the presentation, and this is where we'll kind of start bouncing back and forth, is if you look at a classical 2-socket server, it's really divided into thirds. So if you look at it, the back third of the server is power and I/O. The middle part of the server is CPU and memory, and the front third is generally dedicated to storage. So from my point of view, I'm one of the platform architects in the advanced engineering group at Dell. I don't have a whole lot of room to play with. I can't radically change the sort of ratios of these things. Let me tell you, CPUs and memory are not getting smaller. There's no way. I mean, if Intel had their way, 90% of the box would be CPU and memory. If you look at the back, power supplies, granted, are getting smaller, but customers have this thing about they really want to get data in and out of a box. They don't like boxes that you can't put data into or can't get data out of. So they really want lots of slots, or more slots than just one. So they want PCI slots. They want to be able to put all kinds of accelerators, networking, you name it. They've got all kinds of I/O. So I really can't radically changed the front third of the box to give it more room for storage. So I have to live in this sort of front third area. If you go and start saying, okay, I've got that third to play with, what do I got to worry about? And here's just, just a few things that we have to worry about. Actually, this slide came from Michael, so if you want to talk about but yeah, there's lots of performance, lots of trade-offs. There's performance, hot swap, serviceability, performance, it just goes on and on and on. So we said, okay, now that I know I've got, a certain area to play with, let's look at some of the storage subsystem design considerations. And this is where you start looking at, okay, I've got so many lanes of PCIe I can play with that I can use for storage. Granted, I have to give some of those lanes back for I/O, but newer processors coming out, they have more PCIe lanes than they did in the past. So that's a really good thing for NVMe. Then we have to start playing with, okay, what's the right ratio of PCIe lanes per device? Now, the raw performance of a device is bottlenecked by the number of PCIe lanes. Traditionally, if you look at a U.2 drive, it has 4 lanes of express coming off of it. So you have to balance that. You have to look at it and say, okay, I have 4 lanes of express. What's the maximum bandwidth I can get through that? So I need a number of flash channels on the other side of that flash controller that can give me enough aggregate performance that I can saturate that PCI, that by 4 PCI Express. That's generally 8 or more flash lanes. So, which means I probably need a form factor that can put 8 or more flash chips on it if I really want to be able to effectively utilize that bandwidth. Now, Jonathan, you did this slide. You might want to talk to some of the other considerations.
Right, so just like what Bill was saying, PCI Gen 3, Gen 4, right now we have a by 4, and that's what our U.2 width for PCIe is to each drive. With that's 3.0, as we go to 4.0 and 5.0, it's going to be interesting to look at what is the width. Does it stay the same or does it go down? And the main reason for that is there's a lot of cost from the interconnect, both in just the cabling or the connections, and then also the switching. And so for flash, there's a certain amount of bandwidth you get out of those number of channels that you have, the 8 placements or whatever of packages of NAND. Then with those channels, then the only way usually to increase performance significantly, you start actually raising power. And so we're already in system, as one consideration, really hitting sort of that bottleneck as power is the thermal design. And so that's part of the reason that also you've seen sort of these different form factors starting to come about. Even though we want as few as possible, we really need something that's optimized around the data center systems, something that we've had for the consumer side for a long time with the mSATA, and there's been SD cards, a variety of different, a proliferation of different form factors for client and consumer, but not really for the data center. And so now that SSD is taking up sort of the up notch in the adoption in the enterprise and the data center, where now it's really ubiquitous and it's becoming a very important part of the design, we really have to have something that's more optimized around the system design for data center. It's just about trying to make sure we address all the right needs and the considerations we need. So here I'm also showing like some larger drives attached by 4s that could be like U.2 today. And again, it's bottlenecked by the PCIe lanes to the host. With that same space, we could have smaller drives in a new form factor and have maybe double the number of them, for example, and then have double the amount of connectivity to the host. In that case, we've really dramatically increased performance while still basically providing the cooling that we needed because of the airflow between those. So that's one of the trends you've seen across some of the new form factors is really a density advantage, and then utilizing the performance, really unlocking the performance that's inherent in the number of flash die that you have on a certain SSD design. Another note here is that with fewer drives, with higher capacity by 8, it doesn't buy you anything on the interconnect cost. Basically, if you have 2x4s versus 1x8, is the same amount of interconnect cost or PCI switch or whatever. So it doesn't really help you to have larger chunks necessarily, but you can get higher capacity for a lower cost if you have that same interface of like a x4, for example. Okay, another consideration, so drive power. So your overall system power budget obviously is really important. 25-watt drives with U.2 was a challenge when we first started seeing those versus the 12 watts I think the industry was used to with 2.5-inch. And it's really about unlocking that performance. That was fine, especially for when we were using SSDs as an accelerator, a cache. That's just when, especially even adapter cards were popular in those 25 watts, even maybe plus. But it was really a cache or I/O accelerator. Now we're moving flash to more as main storage. We need to consider the power and the way that power multiplies across the number of devices we have. And so that's a real serious consideration. What is the power per drive, then times the number of drives, looking at how you're balancing the performance again of each drive. Another thing, lower current in your system, in our system designs is really important. I made just some pictures here just to show you sort of the idea of power delivery where lower voltages increase the current density, which makes it just basically, you think of a wire, how much current can you get through a single wire? The resistance, you have to have a bigger wire or a bigger plane, thicker plane, or so on, more interconnect cost if you're going to try to deliver that power. So it becomes more and more difficult to deliver power to the front of a system, especially if we have 12 volts coming in from a power supply in the back of the box, and it has to go through DIMMs and power supply and so on. So higher voltage, like 12 volts, is very useful for system designs for each drive, just to deliver the power to each drive. And then also the power density of the drive versus the complexity and the cost of the thermal solution. So the higher the power density, the higher the power per drive, then it's just that much more difficult to put a heatsink on it. You look at a processor today, and we're getting a lot of value from that integration, but it's harder and harder to cool that single spot because of the power density. So same thing for drives. Flash, thank goodness, is a little bit lower power, obviously, than still in this processor, but the same thing applies. We need to really consider that as a cooling solution overall. We don't have to add additional heat sinking and so on when we don't need to. Also, the drive preheat versus, so in the front is where we want to put these drives so they keep the flash really nice and cool, but then it's heating up the rest of the box. So everything in a server, especially where it's not just storage optimized, then you're heating processors and DIMMs and so on. So that's a major consideration. How much power total do you put in the front? A couple more things, the drive dimensions and the drive spacing. So considering the form factors here, the drive spacing is really important because that's basically your air channel where you can get that air to come in fresh from the ambient, the air conditioning of the room in a data center. And so the airflow restriction is one thing where legacy hard disk drive, 2.5-inch drives have been sort of this block where we block the airflow and then we plug it into a backplane and it blocks the airflow again. And so that's been something that we can significantly resolve with the new form factors. There's new connectors that you allow for airflow without the backplane. And there's really a thinner drive option now for a lot of these where we can allow for greater spacing, but still get the density. And then the other thing is the exposed surface area. So the larger the drive, then the more power you can dissipate across that surface area. So some of the considerations for form factors. So now I'll call up Chris. Do you want to talk a little more about the hyperscale use cases?
Thank you, Jonathan. So what I'd like to do is talk a little bit about how hyperscalers use SSDs today and why we use them the way we do, and then talk about how that drives some of the form factor characteristics that we care about. So follow up a little bit to what Jonathan was referring to. So on the left side of the screen here, you can see a couple of Facebook platforms. So in both, and on the right side is a set of Microsoft platforms. So in both of these, on the top are our compute-centric platforms, and at the bottom are the pooled storage, or what we call JBOFs, just a bunch of flash. So similar to JBOD, which refers to hard drives. What's interesting here is that we've chosen intentionally to use the same SSD form factor across both compute-centric and storage-centric platforms. That was by design because ultimately one of the factors that's very important to us is supply flexibility, right? A lot of times we have capacity that comes up that we need very urgently, and we need to deploy it very quickly. If we have a very specific form factor for a very specific system, then we're very locked in and we can't move inventory or supply around as easily. So we need that degree of flexibility, especially because typically it takes 4 to 6 months to build a new piece of hardware these days. And in a lot of cases, we can't wait that long for a new piece of hardware to show up at our data centers. So ultimately, having the same common form factor is very helpful because it allows us to allocate it where we need it. A question I get a lot is, what about M.2 carriers? So in a lot of the compute-centric platforms, or even in the storage, we put M.2s into carriers. And the reason for that boils down to, why do we use M.2s in the first place? Well, we use M.2s for basically three main reasons. The first one is that M.2s allows us to scale. It allows us to scale capacity, performance, endurance, all of those, and gives us a degree of configuration flexibility that we would not necessarily have otherwise. The second reason is it's a relatively small and intentionally dense form factor. That helps us from a capacity perspective because in a lot of cases, it's more beneficial for us to have smaller chunks that we can scale up and control the overall configuration versus having one giant blob in a physical device that then becomes much more difficult to scale. And finally, flexibility is very important. We really want to be able to install different types of devices, different configurations of those devices. Maybe you want to mix different media types, for example. So having a single slot here that allows us to install any of those options is really beneficial overall from the flexibility perspective. So Jonathan hinted at another benefit here. So he was talking about power density and thermal density. So for us, that is another reason we actually like the M.2s. We've been able to solve the thermal challenges by building some of the customized heat sinks that you can see here. And so the reason the M.2 is nice is because we can distribute that power load, we can distribute the thermal load across a larger volume, basically, and that ultimately works out much more efficiently for us. One of the important factors in our operation of the data centers is ultimately the power efficiency and thermal efficiency. Spinning fans very quickly costs a lot of power and therefore a lot of electricity cost as well, right? So you really want to use that electricity for getting useful work done and not just pushing air back and forth through the data centers. So how does that translate into actual form factor characteristics? What is it that we then care about for the form factor themselves? So I've kind of broken this list into what we believe are the more important criteria, and those are that are a little bit less important to us anyway. So I've touched a little bit on the flexibility. I want to poke on that a little bit more because I actually think it's a pretty important aspect. So in this scenario, what's very important is having a single slot that we can put multiple different types of devices into is actually very important. Think about a motherboard design, right? In many cases, you have, I don't know, 15, 20 different kinds of connectors for any number of different I/O or modules or SSDs or CPUs or DIMMs or what have you. Every one of those can only support typically that one device type that plugs into it, right? So that means I have to predict 4 or 5 years out from now in terms of what my customers are going to need configuration-wise, right? Because I have to lock in now how many slots I need of DIMMs or CPUs or I/O or whatever. And that's very challenging to do in a very dynamic environment that we operate in. Our workloads change, our customer requirements change. So it's much more beneficial for us to have a common set of slots, for example, 16 slots that I could plug anything into. And then we can decide what needs to be there at the time that we need to actually ship the hardware versus trying to do that many years in advance. So ultimately, the next two in some ways go without saying, but because of the volumes that we work with, we obviously need something that can be produced very quickly, very efficiently, and at very high scales, and so that we can ultimately consume it at those scales. Obviously, cost is certainly a factor. The capital expenditure of those devices certainly needs to be controlled. And then I've touched on the power and thermal efficiency. So what that means for us, for example, is rather than shoot for the maximal density that we can get in AU or 2U or whatever your unit of measurement is, in a lot of cases, what we want to do is find the most thermally efficient way to do that, right? So we want to be able to pass the least amount of air through the systems that we possibly can so that we get overall better efficiency. Hot swap is very important. In a JBOF system like that, if you have, a couple hundred terabytes of flash sitting behind the system, if a drive fails, you don't want to have to take all that infrastructure down just to replace that one device. That's another reason that we are interested in the M.2 form factor, not because of the hot swap characteristics, because obviously it's not hot swappable, but because of the unit size that we're talking about, right? The failure domain is very constrained, so if that one device fails, I can go swap it out versus 15 other devices or a huge amount of capacity. So I would take this one as kind of a superset requirement. We obviously have a number of compute-centric applications that are not hot swappable today. And for those applications, it's fine. But typically, if you build something that's hot swappable, then it's usually not hot swappable as well, right? So service is also an important aspect. So what that means to us is two things. One, we need to be able to quickly and readily identify a drive has failed, right? So that can be as simple as we have very consistent LED schemes. We know exactly when the technician goes out, exactly which drive gets pulled. They have to be able to scan a drive very quickly and say, okay, yes, that is really the drive that needs to get removed. And then secondly, when it does actually get removed from the system, it needs to happen very quickly. If you have a huge amount of servers and a very small number of technicians, every time you pull a drive out, it needs to take 10 seconds, for example, cannot require any tools, and you need to be able to install the new drive again very quickly as well, right? They have a huge backlog of tickets that they have to work through every day, so every second that they spend on something is time they could be spending on something else. So in the less important category, are the first two are really around the fact that the 2.5-inch or U.2 form factor has done a great job in the past of providing some of the flexibility that I touched on, in that you could plug in an NVMe device or a hard drive, and you have a common set of slots that work for that. But I think we're at this point now where that form factor has kind of served its purpose, right? We need to start thinking of the future and the future NVMe devices or future I/O accelerators or other devices that are coming down. And we need to create a form factor and a flexible slot that allows us to be able to swap those types of devices in and out. In all of our infrastructure today on the hyperscale side, we already separate flash and non-volatile media separately from hard drives anyway. So that added flexibility buys us nothing anymore, right? Those are completely separate infrastructure sections anyway. So it really doesn't buy us to maintain that backward compatibility that we used to need in the past. And then finally, maximum density. So this is an interesting one, right? Because you would typically think that, we always want more and more capacity. And while there is a truth to that, that's really at an aggregate scale, right? So the problem with trying to continue to pack more and more density into a single SSD is that it has two fundamental problems with it. The first one is from a failure domain perspective, right? If you have an 8, 16, 32 terabyte or higher capacity SSD, and that thing fails, and by the way, the failure rate is not improving over time. It's not magic, right? So if that thing fails, it takes a long time to restore all that data, right? I mean, 32 terabytes pushed through a relatively small pipe, and that's not knocking anybody, anybody in that sense. It's just pure physics, right? It takes a long time to recover that. And so that's a lot of operational mess that we ultimately have to deal with. So we much prefer a smaller failure domain because then we can constrain it and we can distribute the data more effectively. The second problem with the density is that in many cases, the flash is underutilized today, right? So you may have heard the term dark flash. What that basically means is that in many cases, the flash is 40, 50% utilized. So that's 60 to 50% of the flash capacity that is stranded today, right? That is burning power, that is stranded capital expense dollars, that is capacity that we could be using for something more useful. Now, there's a number of reasons behind that at the system level, of course, and there's multiple solutions. I mean, you heard me last year talk a little bit about NVM sets, and that is certainly one of the approaches that we're taking to address that. And there's a number of other ways to help that. But that's kind of a key point. And it's one of the reasons that we went with M.2s to begin with, is because it allows us to stay focused on a relatively smaller chunk size. We know the NAND die density is going to increase over time, so why make the problem harder for ourselves? So ultimately, the ask that we have is, I think what's best for all of us, from a customer side, a supplier side, and everyone that works in this industry, is if we can get to the point where we can reduce the number of total form factors that we ship flash with, I think that's ultimately in everybody's best interest. So our ask is that across the board, we find a way to reduce the total number of form factors that we ship to something reasonable, something along the lines of 4 or less, right? That is something that we can then all align around, and we can build our systems around, and hopefully that gives us enough degrees of freedom for some of the different system design trade-offs that we've got. Talk about client.
So before we get into client, I want to go back and sort of reinforce a couple of things that both Jonathan and Chris said. If you look at a classical server, like I said, the front third is storage. And in that case, 2.5 and 3.5 inch drives have worked very, very well in the past. And if you think about it, you measure storage, at least from the system point of view, on 2 metrics. One is its performance, and the other one is its capacity. So historically, the way you increased performance with rotating media was you added more spindles. So to aggregate the performance across numbers of spindles. They were relatively low performance. With NVMe, I mean, it's the first time in my career that I can build a server storage system that is faster than the CPU. It can pump more data than a 2-socket server can reasonably swallow. So I don't need to scale performance by adding more devices. The only thing I really need to add devices for is to increase the capacity. So I don't know if you can see, but this particular server has 2.5 inch drives, and then it has a section in the middle. It's called expansion. This is where the SAS expander lived, so that I could fit 24 drives into this thing. If you think about expanders were like a necessary evil. They really don't do anything for me. From a customer point of view, they're wasted space and wasted power.
I'm offended.
So one of the problems, both Chris and Jonathan talked about, smaller is better, but you also have to think about how many devices do I reasonably need to be able to put into this thing? And, thanks to Intel, we're getting a lot more PCIe lanes, so we can put a lot more NVMe devices. But if I make those, devices really small, then I've run out of my PCIe lane count, and I really don't want to put switches in there because they take up space, they take up power.
And they do nothing.
Yeah, well, and they do nothing. So from my point of view, I really want a form factor that is large enough that I can put a reasonably large number of flash on it. Granted, I have to worry about the failure domain, as Chris and Jonathan both pointed out. But I also need to look to the future because NAND is not the only technology out there. There are other storage class memories that are coming that I don't really know exactly what they're going to look like. So I kind of want a form factor that gives me a little room to play with in case I want to put a bigger controller or a larger package size or everything. Because right now we've optimized a lot of these things around the current flash size. So I just wanted to get those points in. Now, going over to client, granted, none of us up here are really client people, but the client guys at Dell wanted me to throw these slides in. So the client challenges. Today we probably ship more NVMe storage in client than we do, in enterprise by a long, long shot. NVMe is taking the client space by storm. I mean, at Dell, they're trying to migrate to NVMe as quickly as they possibly can. And one of the reasons is it gives them a tremendous amount of flexibility. If you look at this, they started with 2.5-inch drives in the desktops. They migrated down to the M.2s, and now we're even getting single chip VGA drives that you can solder down in your tablet or your phone and have more than almost a terabyte of storage. It's amazing how much storage you can pack into these things. Now, yes. As the Microsoft guy points out. One of the things that the client guys have generally not had to deal with to date was hot plug in their devices. If you notice, most of the laptops do not have hot serviceable drives in them anymore. And a lot of the desktops don't either. So if you look at what's coming is they're now starting to talk about putting NVMe in SD cards and compact flash. So this is going to open up another large set of possibilities for the client guys. And God forbid they put them in the enterprise, but if they get cheap enough, I'm going to have to deal with them. But it now means that the client guys are going to have to start dealing with hot plug issues on NVMe, which is something we really need to get our arms around. So that was my last slide. I wanted to open it up for questions. And please, when you ask your questions, tell us which intended victim you want.
I think Chris. Okay, so you've more or less admitted that the low capacity M2 is your sort of rich man's NVM sets, right?
Rich man's.
Well, yeah, because
I said nothing about that.
Well, what's more expensive, a 4 terabyte or 4 1 terabytes as far as controllers that you're going to have to pay for? Does the implementation of IOD change your calculus as far as what form factor makes the most sense for your type of operation?
Yeah, Mark. So, Mark, that's actually a great question. In short, yes, it will. Right, especially as we get into QLC-based drives, for example. In those scenarios, it doesn't really make sense to try and pack that into an M.2, right? I mean, that's the whole point, is that you want a lot of capacity, even if it's relatively low endurance. So for an application like that, yes, certainly we're going to want larger form factors in that, and sets and IOD are going to help us consume that most effectively.
No other questions? Sure.
Yeah.
Hello.
So to pick on, Chris again. As a follow-on to that, so you said larger form factors. Are you thinking larger standardized form factors, or is this that by 8 thing? Or I mean, are we getting big now? Or are we,
So
the question.
I think we've created enough form factors, right? One of our design principles has always been there's no value in gratuitous differentiation, right? If there's 2 form factors that are 2 millimeters in difference, is it going to move the needle that much? Probably not. Let's see if we can compromise on something that works for both applications. So in short, where we are is we definitely would like to see one of the EDSFF or two of the EDSFF form factors become the de facto standards, right? I think we've been promoters of EDSFF. We've been involved in the conversations. So we would very much like to see the market gel around that.
So you were asking about size, and I think one of the things that's missing from a lot of the conversation, actually, the sanitize and race, I had a lot of issues with your certification thing because supply chain integrity, re-authentication challenge, but there's a whole slew of things there. And what that speaks to is compute. One of the biggest things Chris and everybody talked about was power. Power is the killer for all data centers. It's the killer for all customers because OpEx actually outweighs CapEx at the end of the day. And in fact, many large data centers, you could replace the hardware every year for the amount of electricity you spend. So one of the things that's going on, and one of the reasons you want potentially a larger mechanical size, so that's why there are different sizes up here from the different standards, is to add in more data-centric compute. So we're going to see more and more, can we light up more flash local to the flash? Embedded RISC-V, for example. You've seen Western Digital announce some stuff. Their CTO said, we're going to do 100 million cores. Okay, it's a million processors, but the point here is you've got, let's say, 20 to 40 million SSDs being done in the data center alone by 2020. In the client space, I'll tell you, my former half of my company that's on the client side was flipped to NVMe entirely for all their laptops, and the only rotating was cold storage. So, client far exceeds, it's hundreds of millions of units compared to the enterprise, but they don't do data-centric. The other things that no one's asked questions about, which surprises me again, is the classic server design had a single point of ownership, single point of access to the data, but we're really entering a data analytics, machine learning, AI, et cetera phase. The notion of one thing accessing data is really absurd these days. So you're seeing new interconnects and other things coming about, or new ways of organizing the way we access these mechanicals. One of the reasons that when you look at the TA1002 connector, okay, it's a 1C, 2C, 4C. So I was one of the people who helped create this thing. We can divide that into equivalent of a by 1 up to a by 16, but we can also treat it as 16 by 1s, okay? And as you get to higher and higher signaling rates, that means you can have 16 different paths out. Or you can go to switch topologies and some other stuff. As much as they may seem useless to you, multi-head or multi-initiator access to flash, access to SCM, access to DRAM is our new reality. And mechanical composability by standardizing the mechanicals and the form factors. I'm actually a protocol guy, but I actually conceived a lot of stuff for these connectors, and that started in 2014 because I got to the point where I'm looking at my protocols and the way I want to organize things. Mechanically, it didn't work. So I've been with PCI Express since 3GIO days, worked on CAM, Revo, all these things because I wanted to embody things differently. You got to start thinking differently about how you access data. Mechanical embodiment is the first phase to understanding how the things are going to be used. We didn't create these form factors because we wanted to be cool, not to differentiate gratuitously. We did them because there are different roles, and you got to start thinking differently about the way data is accessed. So, sorry for my little rant, but you got to start thinking differently about how NVMe semantics and move to more logical views of things, not just one-to-one physical associations. No spice?
And he did not say Gen Z 1.
That's true. I didn't, but you know who I am then for what I do.
I have a question for Chris, if I may. So, of course, Samsung was trying to put their M.3 or NF1 or next gen form factor, whatever it is they're calling it right now. Their promotion on it was that you could stick an M.2 card in the same slot most M.2 cards. And I would think that you'd want that for being able to buy cheap cards as opposed to buying an actual M.3, even though it's not hot pluggable. Why is it that you find that the EDSF is a much better option to fill that need?
So as I mentioned in the slides, backwards compatibility in and of itself is not all that interesting, right? We have a pretty crack team of system designers. I don't need to go off and reuse the same system. I can design something new if I need to. And so the better answer is we need to look long term, and we need to look at what is a more consistent connectorized solution that works better for data centers and multiple potential devices we plug into it. I mean, the M.2 connector, as much as we use it today, is not necessarily the ideal connector or pinout for that, right? So rather than being burdened with that, maybe we should work on a connector and an interface that works better for some of the future designs.
Any last questions?
So a follow-on to that, Chris, what do you see as the next generation connector? Do you see it being an enhancement of M.2 or something else?
It was up on the slide, the 1002, if I get my numbers correct.
Yes.
I think we have consensus.
Yeah, that was actually something I failed to point out, but all of the EDSFF form factors have a common connector that is actually defined in another SFF document, which is 1002. So we spent a lot of time up front defining the connector first before we actually went in and tried to define the physical form factor. So all three of those EDSFF form factors use a common connector.
And just to build on that, actually, OCP is using the connector, Gen Z, Kobo. So you've got multiple industry bodies. There's one other I can't say because it's not public yet, but there's high volume is going to be on that connector. So that's in terms of the data center and memory and I/O and storage and all sorts of stuff. SFF TA1002 is what it'll be. And I'll be doing a talk at the SIG DevCon talking about that connector too.
A new company, well, NGD has come out with processor and storage. And I was wondering how that would impact the form factors, particularly on the power equation side of it. Maybe Michael could address this.
So the form factors vary in the power. If you went to that summary slide, you'll see it. But if you actually looked at, I'm going to pick on TA1008 for the moment, you can have a 25 watt, and if you do a double wide, you can go up to 75 watts. So that's one of the reasons why Bill said there's different sizes, because you're looking at different ways of organizing those. And you can take a double wide and two single wides and replace a double wide in there, and it's interoperable. So there's a lot of thought in each of the connectors. The same thing is on Ruler. There's a 25 and a 40 watt. So it just comes down to what you can pack in and what can you cool, to Jonathan's point earlier. Airflow impedance, and so forth are really critical. So if they put a lot of processing power down into the storage, they're going to need to be, just to be able to cool it and so forth, be able to use a larger form factor. And that's, again, why there's not one size that fits all. The number 4, I used to have a professor who was the rule of 3 for everything. It's actually the rule of 4 for mechanicals for me. But yeah, that's why there's different sizes.
Yeah, let me tag on to that real quickly. So I think in general, what we want to see though is lower power, also the processing. So we're not trying to recreate what we already have with the two socket server today, right? We're not trying to recreate that in the SSD necessarily, right? So lower power processing, and also data, algorithmic, sort of specific processing, more data-centric processing is also what we want to do there, which is lower power intrinsically, right? So you look at like FPGA, or you look at specific small acceleration pieces of code, snippets of code. That's really what we want to see also, not just high power like what we see with a two-socket system today. So I think actually we can fit integrated a lot of the processing into smaller form factors as well. I think it's really just a matter of your capacity and what the power envelope, again, what type of system you're trying to cool it in, all those specifics of the system.
So a lot of MIDI controllers actually have embedded ARM or you're seeing now some coming with RISC-V. So put it in perspective, you can build a very nice data-centric processor with 14K gates. So that's easy from a silicon budget to put into your media controller and create data-centric. So in addition to just having management processors, you can create specialized, which is why a lot of people have been looking at RISC-V, because they can then tailor those. Maybe you want to do a machine learning specialized storage subsystem, you might be able to download something relatively general purpose, but not recreate a full x86 experience. So again, mechanicals will vary based on what you're trying to do, but the media controllers can integrate processing fairly easily these days.
So I think we have time for 2 more questions. Anybody want to go forward? Other way?
So this is a form factor and it isn't form factor. I talk about power loss protection in the 30%. It's about 30% of the board area, about 30% of the design time, and it's about 30% of the bugs that you guys find when you're evaluating our drives. So the question I have is at the system level, is it hard for you guys to figure out something around a system power loss protection as opposed to us trying to, embed 20, 30 little capacitors on an M.2, or we've even joked on 1U long of inserting a cell phone battery into the thing.
So one of the issues with that is, yeah, we've kicked around the idea of doing a system level power loss protection, and that only solves half the problem. The problem that it solves is if your system loses power. The problem it doesn't solve is if somebody, let's say a drive fails and your service technician had a few too many beers the night before and walks up and pulls the wrong drive out during while data's in flight. The data that is cached on that drive all of a sudden goes away because it doesn't have power loss protection. So that's one of the things that we haven't been able to figure out is how do you solve the surprise removal issue?
Yeah, so I have a comment.
Yank out the wrong drive? I'm sorry, the question was, do you assume the data's okay when you accidentally yank the wrong drive, or as Chris said, you go back and reformat everything, reload everything on it?
Well, that's if that data is cached. What if that data only exists on that drive?
Way to stir things up, Steve.
Yes, they're okay. If you want to go that route, then if you're doing a RAID 5, if you pull out, you have a drive failed, you pull out the wrong drive, you've now failed 2 drives. So now you have to have RAID 6. And if it's truly lost that data, when you plug it in, you have to rebuild the entire logical drive. You can't assume anything's good on that thing anymore. So depending on how big your drives are, it could take you days to rebuild that thing.
Any last question? Anyone?
Just a quick comment based on that. So to your point, in SSDs that are not, surprise removal, like what Bill was saying, that's the main feature that customers still are asking for, and so that's why you have to be able to support it on the drive. I think if there's a drive that's inside the system that's sort of it's not hot pluggable, then you can have that feature and no problem. In fact, there's a lot of different ways you could do that, so that's a smart idea.
Thank you so much to the panel. And no one wants to be up here with me. Run away, Mike. Mike's scared of me. No. I'll have some ask. I wish you would stay with me. I'm gonna get lonely up here. Thank God. No. So we've learned that I should not be a runner of mics because I stink at it, right? Basically. But thanks so much to the great different talks and panels. It was all very informative. All of this material will be available on the nvmexpress.org website, so don't worry, you'll be getting all of this. And thanks so much. We wanted to just thank everybody, and please give us feedback about how we can make the Developer Day, and for those of you that were here yesterday, make it better for next year, and keep growing NVMe together. So thanks so much.